Black holes have been predicted for over a century. Since then, we have detected the gravitational waves of a black hole merger and even gotten some photos of these colossal objects. We can do this because we understand how mass, charge, and angular momentum affect the shape, size, and properties of a black hole using the Kerr-Newman metric. Ever since the dawn of the 20th century, it has been known that space and time as we observe them are actually emergent phenomena of a unified spacetime. Just like the surface of the Earth, spacetime is not flat. This means that angles don't obey the geometry that you learned in high school, but instead require the input of a metric tensor to describe the geometry from point to point. The flat version of this is the Minkowski metric. If instead we look at the trajectories according to a curved metric, we find that it behaves precisely the same way that gravity does. The Einstein tensor is one way to encapsulate the curvature of spacetime. It is an intricate transformation of the metric which it can be solved for. The stress-energy tensor encodes the flux and density of energy and momentum within spacetime. Einstein showed that these two tensors are proportional to each other, indicating that matter warps spacetime.
If we ask, how does matter change flat Minkowski spacetime, we find through the Einstein-Maxwell equations that it looks like this, where capital R is the distance from the center of mass, lowercase r is a related radial coordinate that follows this equation, a is the specific angular momentum, x, y, and z are the coordinate locations, and m, q, and j are the mass, charge, and angular momentum. If we take any of the three parameters, m, q, and j, to be 0, we get the special cases of this solution, but all are explained by the Kerr-Newman metric.
In analyzing this metric, something strange happens when the density becomes sufficiently large. Within some region A, in this case, there are no sub-light-speed paths starting inside the region that can ever escape. This means that even light is trapped within the region, rendering it black. This is the black hole. In the case of a black hole, the Kerr-Newman metric says that there are 4 regions with special properties. The boundary of the outermost region is a pumpkin-shaped surface called the outer ergosphere, which contains the region where space-time is rotationally dragged faster than the speed of light, requiring all objects to orbit and making it impossible to be stationary. The next boundary is the event horizon, which requires faster-than-light travel to escape from and contains closed space-like curves. The third boundary is the Cauchy horizon, which contains closed time-like curves. And the innermost boundary is the inner ergosphere, which contains the ring singularity of the black hole.